lithium, for example. It's atomic number 3. It has 3 electrons and 3 protons. There are 2 in the 1s level, and there's 1 in the 2s level. So there are 2 electrons here, 1 electron there. And this is due to something called the Pauli exclusion principle, which probably you've heard before, which the most fundamental way of saying it is no 2 electrons can have the same quantum state in the system. But as far as energy level goes, you can have at most 2 with opposite spin. So I can have 2 here, then I go up to the next level, and for lithium there's only 1. So that's what the energy levels look like. And quantum mechanics tells us that I can only have electrons in those levels, right? And they can only exist at those energy levels. So as I go up, this represents higher and higher energies. Keep in mind this is schematic. Now, the Pauli exclusion principle says I can only have 2 electrons here and 2 electrons there, so on and so forth. What happens if I bring 2 atoms together? Well, that would seem to violate the Pauli exclusion principle because I have 2 of these. But what happens is these 2 atoms interact and these levels split. And so this is schematically what you might see. There are now 2 2s levels and 2 1s levels. As you bring more and more of these atoms together, you get more and more splitting, and the difference between these split energy levels gets smaller and smaller, and eventually you may see something like this. This represents, say, a one-dimensional array of atoms. That this is the 1s level, this is the 2s level, but there's so many of them, they're so split. If you have a real piece of material, you may have, for example, silicon has on the order of 10 to the 22nd atoms per cubic centimeter in it. You can imagine the separation is so small that even at near absolute zero, electrons can move back and forth through those energy levels very easily. So we think of these as bands now, that I can have electrons or states anywhere in that range and anywhere in that range, but I'm separated by forbidden ranges of energy. You'll never find a stable electron there. You can find many there, and you can find many there, but none in between. And this is a consequence, essentially, of applying Schrodinger's equation to this potential. Now, what we'd have to do is come up with a mathematical formulation for this potential and plug it in for V of x. And it would be kind of nasty. So what we do is we use something called the Kronig-Penny approximation, and we approximate those Coulombic potentials as little square wells. So now they have 2 values, and it makes it very easy. And so this is just sort of a picture of how we represent this in an easier to formulate way. And so we plug that V of x here, solve the equation under certain boundary conditions, which we won't go into, and I want to show you what the result looks like. What you get is an equation that says something like cosine of k times a, where a is the width of one of these wells and k is the wave number, which is 2 pi over lambda, equals a very, very complicated equation that's this long. And it has lots of hyperbolic trig functions in it. And so those 2 sides of the equation have to be equal. Well, one of them is a simple cosine function. And cosine varies between 1 and minus 1. But the other side of the equation looks like this. And so the idea is those 2 sides can only be equal when both of them are somewhere between minus 1 and positive 1. Otherwise, it's not a solution. And so the idea is as we plot this as a function of energy, we see that there are some allowed bands of energy, and then there's a disallowed band of energy, an allowed band of energy, a disallowed band of energy, and on and on and on. And so we see this picture of bands of possible states separated by bands of impossible states. And the idea is that they're not a solution. And interestingly enough, if you look at the detail, the way you explain this is these forbidden bands are areas of Bragg deflection of these probability waves where you get destructive interference. And so there's no wave, there's no energy, there's no solution. Then if you go back and look at, I said one thing you can get is a wave function, one thing you can get is the value of the energy. If you go back and look at the energy equation, it's also very nasty. But it looks something like this. Let me try to explain this. If you had a free particle just sitting out in the vacuum and there was no potential, then your Schrodinger equation would be pretty simple because that would be 0 and you just get a simple sine wave. And the energy equation would look like this. It would be proportional to k, where k is a wave number. It's just a way of writing inverse wavelength. And it would look like this dotted line. It's just a parabola. It's kind of easy to imagine. So it's a dispersion relationship. Energy is a function of K. But if you look at it with the boundary conditions of the well, what you find is, as you start to somewhat follow this picture, but when you get to values of K that are integral numbers of the lattice spacing, that's when you get your destructive interference, and you get a jump of disallowed values. And then you have to jump up to this level, and then you jump up to that level, and then you jump up to that level. And it's always an integral number of the spacings of the lattice. And so all these things vary with K-space. K-space is very periodic, so you move them all in to the first period, if you will. It's like having 10 periods of a sine wave. You only need one because they're all repetitive. And so then what you get is a band structure in so-called K-space. It looks kind of weird. It's hard to imagine what it means. But it shows a gap of disallowed energy separating bands of allowed energy. And we'll come back to an interpretation of that in a minute, but it's easier to think of this in terms of real space. So let's jump back a minute and go back to our known energy levels and look at it in what we call real space. In other words, what we're living in now as a function of x. So we already know, based on the wave nature and boundary conditions of electrons in an atom, that those electrons can only exist at certain discrete energy levels. We've already seen that. We showed it with those Coulomb diagrams. Now we're thinking E is a function of x. Now you bring two atoms together and you get the splitting due to Pauli exclusion principle. You bring many atoms together and the splits are so close, again, you get bands of energy separated by gaps because they're very, very close together. Similar thing that I just showed you with those funny funnel diagrams, but now this is in real space. So the result is many bands separated by these so-called forbidden gaps. So another way to look at that is if you have a solid material, you have a band of allowed energies, a forbidden band, a band of allowed energies, forbidden band, on and on and on. In principle, they're limitless. And the higher the atomic number, the more of these bands that are occupied. So, for example, hydrogen, has some electrons here, but if you go up to higher and higher states, you keep jumping higher and higher. So what we see is allowed energy bands separated by energy gap. The lower levels fill first. And so the lower electrons are tightly bound. So if you take a material like silicon that has many of these levels, the lower levels, those electrons are so tightly bound in the atom that they're not going to have any effect on electronics. We don't really care about them. We usually only care about the highest band, which could contain electrons, which is relevant to the valence shell of the atom, and the next one. And the reason is this. So this is the way we would represent sort of a real space band diagram. This is the highest band of allowed energies that actually has electrons in it at absolute zero. It's called the valence band because it's due to all the electrons in the valence shell of the atom. There's your forbidden gap, and there's the next possible band of allowed energies. Well, from a device point of view, this is what we're interested in. We don't care about these lower bands, and we don't care about those higher bands, because in essence, this is where electronic behavior occurs. So this probably isn't the best order to put these in, but let's look at the valence band first. The valence band contains the valence electrons from the valence shell of the atom. Right? The energy gap is forbidden to electrons. The next allowed energy level we call the conduction band because it's normally empty or mostly empty, but a certain amount of energy can be applied to the system, and an electron from here can go up here. In other words, it can jump this forbidden gap and go into this so-called conduction band and exist there because there are many, many empty states there. And so that's what gives rise really to electron conduction in a semiconductor, and actually also in an insulator, is knocking electrons across this forbidden gap into the conduction band. This one's largely full of electrons. This one's largely empty, so there's a lot of energy space for it to move around in. So this is typically the way we'll draw a band diagram for a device. Actually, we'll get to the point where we only draw that line and that line, because we don't really need to think about what goes on above those lines. It's just the gap. So we can look at this from another perspective too. All this fits together. And I know I'm throwing a lot at you at once. This takes me weeks to do in my class to get to this point. But another way of picturing this is from a sort of a chemical bond point of view. So we call this the bond model. Imagine this is a silicon atom. That's the nucleus, and these are the various orbital levels. I just drew two of them. And so this represents the outer shell where we have electrons. We call it the valence shell. There aren't any electrons any further out. And there are two silicon atoms. And it's those valence electrons that give rise to chemical bonding in chemical and mechanical and thermal and electronic activity. And silicon crystals bond together via covalent bonds, where you basically share two electrons. So here's a case where these two silicon atoms are bonded together covalently, and they're sort of sharing one of their valence electrons. So I could have another silicon atom here, here, and here, 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 and here, and basically get four bonds. But I just drew one for illustration. So this leads to another type of visualization where we, instead of drawing all these circles, we draw, SI, and these lines represent the two electrons in the covalent bond. So imagine a lattice diagram of zillions of these guys, and they're bound together by these two covalently bonded electrons. At T equals 0, silicon is a really good insulator because all the valence electrons are in a covalent bond. So where are you going to get current flow? You're not going to get any electron movement because they're all bound, and you get no current. But as the temperature rises, let's say room temperature, then energy is distributed in a statistical way throughout the lattice, and some of that energy gives enough energy to these bonds to actually break a bond. So let's say this electron can escape the bond and move out in free space. I've illustrated that here. This blue circle with a negative sign in it represents an electron, and it's left its bond. Okay, so now it's in the free space and it can move. If you apply a voltage or a field, that electron will move and that gives you current. But it leaves behind an uncompensated bond. And I draw that with the square root of positive sign because now I've got a net positive charge due to the core here. The interesting thing is, it's easy to imagine this electron moving around in the free space between the atoms, but what's a little bit harder to realize is that this empty bond here can actually be filled by adjacent electrons in other covalent bonds. So for example, this electron right here could move over into this vacancy, and then that bond would be compensated, but this one would be uncompensated. And other electrons can move in, and what you see is the position of that vacant bond can move. It's charged, and so you get moving charge, so you get effectively current. It also gives rise to something some of you may have heard of called Bremsstrahlung radiation. People have measured it from accelerated positive charge, just changing position. And so we call that a hole because we think of it as an empty bond or an empty state. And in a semiconductor, both of these charges move and both give rise to current. It's just that one of them, this represents an electron in the conduction band, this represents an electron in the valence band, but we call it a hole. So the idea then is this is kind of messy, but there's my band diagram. There's the top edge of the valence band, the bottom edge of the conduction band, and that's the energy gap, the forbidden energy between the two. And for silicon, this is about 1.1 electron volts. It's equal to the energy width of the forbidden energy space between those two bands, but it's also exactly equal to the energy required to break that covalent bond, which in silicon is about 1.1 electron volts. So a band gap is also, the difference between the energy difference between two allowed bands. It's also the energy necessary to break a bond in the material, in the atoms that make up the material. And so when I do that, I get a quasi-free electron up here in the conduction band, and I get a quasi-free hole. They're quasi-free, they're still influenced by the material. I get a quasi-free hole here. If I apply a voltage or apply an electric field with a vector force in that direction, electrons go in the opposite direction, holes go in the same direction. This is positive, this is negative. So applying a field, temperature gives me an electron and a hole, called an electron-hole pair, and the applied voltage of the field causes them to move and it gives me current. And the interesting thing is in a semiconductor I get two sources of current. I get electron current and I get hole current. This is the motion of vacant states, but it's actually the motion of the valence band electrons. And this is just motion of the electrons. But we call this a hole because it's a lot easier to keep up with that vacant state than all the 10 to the 22nd per cubic centimeter electrons that make up the valence band. And quantum mechanics tells us that I can consider that a particle, and the only difference is the charge and the mass. Okay, so in any case, once I get my electrons up into the conduction band, I can write a current density equation that says current is flux times velocity. N, which means negative, is the electron volume density, the number of electrons per unit volume that are up here. Q is the charge on each of those electrons, and it's negative. So that gives me my number of electrons per unit volume times the velocity that they're moving in that electric field, and that gives us the current due to that applied field. We call that the drift current because we say the electron is drifting in the field. You can also write a whole current density equation that's analogous to that. But anyway, that's essentially the way conduction works. Okay, so let's take this a bit further and look at some examples. This I pulled out of the textbook, and it's not the most beautiful drawing in the world, but the shaded area are filled states and the lines are empty states. So first let's look at case C. This is equivalent to what I said about a semiconductor. This is like silicon. At absolute zero, this band, the valence band, is full, and this band is empty. If I apply energy, I can get electrons to jump across. Now this can represent a semiconductor or an insulator. The only difference between a semiconductor and an insulator is the value of Eg. An insulator has a big one, and the semiconductor has a moderate one. And to give you an idea, this could, for a semiconductor, could range anywhere from half an electron volt to maybe 4 or 5 electron volts. You know, it's a gray area. Whereas an insulator, this might be 8 or 9 or 10 electron volts. And really, that's the primary difference is the size of that gap. These both represent metals. This is a case where the valence band is only partially full. If the valence band is partially full, that means it's partially empty. There's lots of empty states, and the valence band electrons can move around in it freely. And so you could argue whether we should call that a valence band or conduction band. It's really just a matter of nomenclature. There are other metals that band structure calculations show that have a zero energy gap. They're actually overlapping. So this band moves down here, and you see there's overlapping states, and so electrons can easily move back and forth. So metals, in essence, kind of have no energy gap. That's one way of looking at it. Semiconductors and insulators, they have an energy gap, and the difference is just how big that gap is. Now that I look at this, I'm not even sure why I threw this in here. It's just another picture of band structure of a semiconductor in so-called real space. It's E versus X. There's the band gap. This is something we're not going to have time to delve into a lot, but it's called the Fermi level. It's really a reference energy. It's the maximum energy that an electron would have in this structure at t equals 0. But it's a reference energy that is kind of difficult to explain in a few sentences, but again, it's just a reference. Now, this is an EX diagram. Now we go back to the EK diagram, and we can get a view of why E versus K can be useful. This is two examples also from that textbook. Here's an example of what we call a direct band gap semiconductor. The minima, again, this is E versus K, the minima of this conduction band and the maxima of the valence band line up at the same point. And so transitions of electrons from here to here or here to here are direct. And so if I have an electron that falls from the conduction band to the valence band, where does that energy go? Under the right conditions, it can go into a photon and produce light. And so a direct band gap semiconductor can be used as a photoluminescent or a photovoltaic device. And we make semiconductor lasers out of them. Silicon, unfortunately, in some ways, is an indirect band gap semiconductor. Notice that this guy's minima and that guy's maxima are separated. They have different values of K. So we said they're separated in K space. K is related to momentum. And the idea is for a transition between here and here, not only do I have to lose this energy, but I have to have some kind of interaction with the lattice, say via phonons, that cause the momentum to change. And so the point is, in semiconductor, in silicon, when this happens, most of that energy is given up to lattice heating. And it's very difficult to get photon emission from silicon. Not impossible, but not very easy. And so I can only see this in K space. I can't see this in real space. But then when I start, next time we talk, looking at devices like diodes and transistors and looking at their band diagrams, it's difficult to see how they work in K space. It's easier to see how they work in real space because they exist in real space. So we need both types of diagrams. Talk a little bit more about one way to look at a whole, sort of a fun way to look at it. If you look at this table with 5 seats, and there used to be a person sitting here, but they got up and left and went upstairs. So if you think of the people as electrons and the empty seats as a whole, that person leaving and going upstairs into the conduction band left a vacant seat here. Now, if Brian moves to the left, then the vacant seat moves to the right. If Vanessa then moves to the left, then the vacant seat moves to the right. Now you can look at this as the ensemble motion of all these people, or just think of it as the motion of that moving seat. And so if you think of that as a whole, that's one way to look at it from a state point of view, what happens in whole transport. It just changes its position. It's really people moving. It's really people moving, but you can model it as an empty seat moving. And it just is easier to keep up with one empty seat than it is 4 people. So that's sort of a either here or there. So any questions on this? A lot of concepts to throw out. And I think in the next talk I give, which is 2 or 3 weeks, we're going to apply this to real devices that will maybe make a little bit more sense. The last thing I want to talk about, there's still a few more minutes, so let's go ahead and finish this, is now that we've talked about the band structure and where all this comes from, how do we actually model conduction in a semiconductor? You've got a piece of semiconductor, I apply a voltage to it, current's going to flow, we know this, we make measurements. How do we actually model that? It's actually a very complicated model that leads to something called the drift diffusion model, and I'm going to qualitatively tell you where it comes from and then just show you the results. Again, here's the same band diagram. The idea is thermal energy produces electron-hole pairs. A covalent bond is broken, or an electron is given enough energy to jump up here in the conduction band, which is relatively empty. This band's relatively full. It leaves a hole. I apply an electric field, electrons go that way, holes go that way. The idea of this is from this basic equation for the force on a charge. If I apply an electric field, it's a vector, to a charge of minus q, the force on that charge is minus QE. If the charge is positive, it's positive QE. So for electrons, E, that's what the force equation looks like. For the holes, H, it's the same thing, I just have a positive sign. So electrons go that way, holes go that way. But keep in mind, though, the conduction band electrons are going that way. If the holes are moving that way, that means the valence band electrons are going that way. So really all electrons are going in that direction. We're just modeling this hole. So how do you come up with an equation for current so we can predict the way devices behave? The drift, there's 2 terms. There's 2 types. There's the drift current and the diffusion current. Drift current means it's electrons moving in an electric field. So it's just like basic circuitry. You apply a voltage, current flows. So let's, excuse me, we'll talk about that part. The other component's a little bit more obscure. But a drift current is just flux times velocity. The flux is the charge times the number of carriers per unit volume. How many electrons per unit volume I have are in, and the charge on each of those. And you multiply that by velocity. So I need to know how many electrons per unit volume I have up here in the first place, and we call that N. How many of them are there? Well, Q times N times the velocity will give me that current density, current per unit area. So how can I figure out how many electrons are there? Well, it depends on a lot of things. It depends on that band gap. It depends on the temperature. It depends on how many empty states there are up here, because there are only a finite number of possible states that can be occupied up here.